So, in this lecture we are going to talk about MATLAB model development for digital hysteresis current control. So, here we will first talk about custom MATLAB model development for mixed signal hysteresis current mode control, and then we will consider few MATLAB simulation case studies. So, first we will recall our mixed signal hysteresis current mode control in a buck converter that we have discussed in the last week. So, this is the generic representation where you need to have one AD converter for the voltage loop is in digital, and then this is the compensator. So, typically you take a PI controller, then you need to have a D2A converter. So, we can use a single DAC or you can use 2 DAC. So, this is for basic conceptual realization, and the inductor current in analog. So, this is the whole block is in the analog domain, and so we have discussed about detail, but this can be realized using one DAC as well as one comparator, and that has been discussed in this paper. Now, this is a hysteresis band which is in digital domain. So, we can customize this band in order to regulate the switching frequency. If we talk about this approach, so first we need to have ADC. This ADC actually sample non-uniformly, that means where are you going to sample. So, we can have, if you go for a peak current mode version, then we can sample the voltage at the valley point. If you go for a valley approach, then you can sample at the peak, or in fact we can take the sample 2 times peak and valley, but here we are discussing we are sampling once per switching cycle. Now, this ADC we need a sampler, quantizer and delay, and here it is not TS, so it should be an event based clock, because even if we use an uniform sampling, it will lead to multiple limit cycle oscillation. So, it should be event based sampling approach. So, that means this event we will create. So, here we are not talking, it is a general representation of ADC, but this TS here is a sampling time which is going to vary. That means it based on the, I will not fix the time, but I will fix the event, and that event will be created by this trigger pulse. Then we can consider a quantizer and delay. Okay. So, but in this MATLAB realization we want to make it simple, no delay, no quantization. It is just how to realize event based sampling and how to realize a mixed signal hysteresis current control. Now, after this ADC, then followed by quantizer, it is the generic realization, then delay, we can have an error block. Then after this error block we can have a controller. So, if you take a PI controller, and we have discussed that this controller has to be realized by a difference equation. So, it is a clock synchronized difference equation. Okay. Next, that means if we realize this PI controller, I will go to the MATLAB and show. Then next part is that you will generate the reference current, and since we are using MATLAB, but typically this is digital, we need to add D2A converter. So, DAC. So, in DAC in MATLAB you can simply use a scaling function, but in actual realization you need to consider a D2A converter. Then after this DAC we have to decide what technique are you consider. Are you going to use a peak current based approach, valley current based approach, or average current based approach. So, if we go for peak current based approach, then the reference current, that means whatever reference is coming, I am saying that output of the controller followed by DAC, this is my reference current. Okay. So, if we take this reference current, when I say we are talking about peak, so this is my peak current which is set to the reference current, and my valley current is simply Iref minus delta IH, because let me write here, sorry. So, my I valley, this is my I valley which I am writing Iref minus delta IH. and I want to keep the inductor current within this band. Okay. So, here this peak means the controller output is directly controlling the peak current. In fact, if you want to use let us say a fixed current reference, that means a constant current reference command. So, inductor current will just track it on the peak value return. And we have discussed in the last week, since we are doing event based sampling, the hysteresis band and the actual current ripple, they will be identical in this case, because even though there is a ripple effect in the output voltage, that will be discarded because of event sampling, and under steady state there is no ripple effect. So, your current hysteresis band and the actual analog current is same, provided that if we do not consider any propagation delay. In case of a delay, you can get some additional current here because of a delay. So, that means your actual current ripple can be slightly higher than the reference band due to the delay, comparator delay and other things. But in general, if we take the ideal case to start with, you can keep the current ripple and the hysteresis band same. So, this is also discussed here. Now, in MATLAB, I mean actual realization, as I said, a reference you directly set as the peak value. Whenever, that means this is the current, whenever inductor current hit the peak, then you reset, that is why it is reset, and whenever it hit the, that means inductor current hit the value, then you again set it. That means if I draw neatly, that means let me draw this one, and green. So, here it will reset and here it will set. Okay. And here you are using reference. So, reference is directly keeping the DAC output. Now, if you do valley, that means we will directly use this reference current, that means we will directly use the reference current. This is my I valley is set to I ref, and inductor current, and that means the peak current will be here I peak, and what will be I peak? It is nothing but I ref plus delta IH, and your inductor current will be simply within this band. So, you can realize this using this algorithm, and we can adjust the hysteresis band. Now, we can realize using Simulink. I am going to show the peak current, but you can do valley as well as average. What will be the average? In case of average, that means if I take this peak and valley, that means this is my peak is I ref, which is the controller output, plus delta H by 2, and my valley is nothing but I ref minus delta H by 2, and then we will keep simply within this. So, that means we can precisely control the inductor current average value, and this is, you can set it is equal to your set value. That means we can maintain it. The average value of the inductor current we can keep, perfectly track the reference current if the current loop is stable, that means if we repeat under steady state. And we can implement by using the reference current given, adding delta H by 2 and subtracting delta H by 2. So, this is the overall MATLAB block diagram, and that I am going to show. And if you go inside this block, that means if you inside, first you will have a event trigger ADC. So, this is the ADC for voltage loop, which is event trigger. Then you will generate the sample voltage, that is compared to the reference voltage. This is my error voltage, and this error voltage goes to the PI controller. This realization is exactly same as our earlier realization, but only the trigger clock will be different, because it is a clock synchronized difference equation. And if you go inside the hysteresis block, I am talking about this hysteresis block. That means if you go to this hysteresis block, what is there? It is the same as analog hysteresis control, and where we need to set a delta H, and here we are using the peak base peak current based, that means peak current mode control. So, reference current is directly compared with the inductor current to generate the reset pulse. And for the valley current, so this one is our peak current and this one is our valley current. When the current reaches the valley current, then switch is turned on. So, it is a set pulse, and this is a delta H we can adjust to achieve the desired switching frequency. And the output voltage realization, controller, PI controller, this is we have been discussing for many classes. So, that means clock synchronized difference equation where the trigger signal is different, and we are going to MATLAB to see what is the trigger signal. So, this is a mixed signal hysteresis block. If you go inside, we have discussed this is my event trigger ADC. Then this is my hysteresis block, that also we have discussed. And now the event we are creating is the peak. That means whenever the inductor current hit the peak current, that time we are actually sampling the ADC, so that we can actually update. So, here the sampling point is selected as the trigger point. That means if we go to our realization, if we consider this is my peak current reference, if we consider our peak current reference to be, if this is our I ref, and if we use the inductor current where we have a valley here. So, this is the point we are taking, this is the point, this is the clock. So, this clock is our this event trigger clock. Okay. So, we can select this clock also, but there are other aspects of stability, but I think you can, and in fact you can also delay by one sample, but you will also get some impact in terms of transient performance. So, that means here we are using this event clock, and this event clock is used to realize this, and that we have discussed multiple times. So, I am not going to spend time on that. So, we want to run few simulation case studies. That means we want to show that hysteresis control will never become unstable for wide input voltage range. We are making a load step transient. So, we have set a very high proportional gain. So, let us say now let us run a simulation case study. So, we are making a load step transient of 20 ampere, and this is a, so what we have said is that the hysteresis current band is 2.5 ampere. So, you should expect that the actual current ripple should also be 2.5 ampere. So, let us go and check. If we go and check this band first, so you can see it is varying between just above minus 0.5 and below 2.5. So, that means if you shift up from 0, it is exactly 2.5 ampere. And if you go to the higher side, here also it is just above 19.5, below 22.5. That means if you take from 20 to 22.5, it is 2.5 only. So, it is also maintaining 2.5 ampere ripple, and we can improve the transient response very fast, but here I am just showing that case study, and you can see first thing, and I am showing that the sampling process. So, if you go to here, we are not considering any delay, but it is the event based sampling. So, let us say when there is a transient, you can see depending upon how it is hitting the band. So, you can see the sampling point is getting changed. That means the voltage is sampled here, when it changes here it is same. So, it is getting updated here. So, that means you are getting the, it is like a variable time solver, a variable time sampling, because you see the duration of sampling is varying based on the time period of the hysteresis controller. That means instantaneously the time period is varying when there is a transient, but when it reaches steady state, then it is more or less fixed, and then your output voltage sample also get fixed. But since we are sampling at the peak value of the output voltage, you see the peak value is regulated to 1 volt, but your average voltage is actually lower. So, you may suffer from regulation issue. So, you have to address this issue, what should be the right sampling point, otherwise you may lose the regulation point. Similarly, if you use a valley current based, valley voltage based like a valley hysteresis current mode control, and if you take the sample at the valley point, so the voltage will go up. So, that means your valley point will be regulated at 1 volt, but the average voltage can be higher. So, here it is lower. Now, if we go to, let us say we want to change the input voltage, let us say we are going for 1.8 volt for 1 volt output. So, let us run the simulation and see. So, there is no current loop stability as such, but yeah, of course, there is a transient issue, but you can see the output voltage ripple is still maintained at almost 2.5. So, you can see same, there is no change in the output inductor current ripple is maintained, but time period is drastically varying. So, you can see it is more or less approaching towards 3 microsecond, where our desired time period was 2 microsecond. So, your time period has increased or the frequency has decreased because you have decreased the input voltage, but yet you have maintained the same current ripple. But if you take a regular DC-DC converter fixed frequency, what happens? If you keep on decreasing the input voltage, then what will happen? The current ripple should decrease, and if you increase the output input voltage, the current ripple increases for the fixed frequency control. But in case since you are keeping the current ripple same, so naturally the time period is increasing. Okay, so that means it is a variable frequency operation, and you can adjust the hysteresis band if you want to regulate the output voltage, but you can see the response is pretty fast. Okay, and you can get ultra fast because hysteresis control is considered to be one of the fastest control. But how do you make a digital control realization? So, this is one of the example using mixed signal hysteresis control. We can also take one case study of reference voltage transient. So, that means we can take 0.1 and we can now use, let us say, 12 volt input. Okay, so, this is another case study. So, here you can see the response is very fast, at least like a very fast transient response. Again you can see the sampling rate is actually varying, if you consider that in between intersample. So, this may be a problematic because if there is a large transient and if there is less number of event, then your sampling is actually rate is reduced. So, and in fact, we have discussed in the research paper that if we, because this may even sometime even if you further increase, the voltage may collapse because you may not get the actual output voltage information. So, the best way, if the sampling duration exceed a certain threshold value, then you can do a forceful sampling. So, that means we need to combine event based and uniform sampling during the large signal transient, so that the output will not collapse, as well as you can maintain the fast transient recovery. But when it comes close to steady state, we can actually go for event based sampling. But in this course we are not discussing this because these are the very advanced topic. Here only thing you can remember that we are using throughout the event based sampling, and we can get a very fast transient response, and it is also evident from the inductor current waveform. Okay. So, that means we have discussed the various case study under peak current based mixed signal hysteresis control. So, in summary, we have discussed custom MATLAB model development for mixed signal hysteresis current mode control, and we have also considered few simulation case studies. And I think so in this next week we will talk about MATLAB like a modeling of digitally controlled converter. So, this way we will more or less we are going to finish the MATLAB model development for various digital control architectures. That is it for today. Thank you very much.